Okay, we're going to talk about lenses and vision. And we're going to go through ray diagrams again really quick um, because um, it'll be relevant. That's why. So let's remember how we find the image when we have our object here, and this one is a converging lens. So we start with the ray that enters parallel to the principal axis, which again is through the middle of the lens here, so it's this line, and then exits through the far focal point. So red, it's going in parallel, and then it's going to come out through the focal. Then we have blue one, which just goes through the center of the lens and doesn't bend. There we go. And then the last one, purple, enters through the focal point. So it's going to go through here, and then it's going to come out parallel. So through this focal point, coming out, oops, parallel. And that's where our image is. And it's inverted in this case. Okay. Now let's do a diverging lens. Same ideas here, just slightly varied. So it enters parallel to the principal axis, red, same thing as before, but then it comes out, instead of going toward this far focal point, it's going to look like it came from the near focal point. So see, it's angled like that, and we can even kind of project it backward. Then again, the blue enters through the center and doesn't bend. Easy. And then the last one, it enters toward the focal point and exits parallel to the principal axis. So it enters as if it would go through the far focal point, but then it's going to exit, it's going to come out parallel to the principal axis, and then we project it backward to see where our image is, which is here. It's upright, and because it's on the near side of the lens, as in the side that our object is on, it's a virtual image. And in the case of an image like this, you would have to, so with a real image like the first one, you could just put a screen where the image forms and see it. That isn't the case with a virtual image. You have to actually look through the lens to see the virtual image. Okay, now we have a converging lens, but it's closer than the focal point. So it still enters parallel to the principal axis, the red does, and then exits through the focal point, but we'll have to project backward to find our image. So we're projecting backward. Blue, again, through the center, doesn't bend, and again, we're going to project it backward. And then purple, it enters as if it was coming from the focal point. So as if, because this is a converging lens, so it's the near focal point that we're thinking of for the purple ray. And we'll see again in the diverging lens, it's the far focal point that we're looking at for purple. Anyway, so it goes in as if it came from this near focal point, but it comes out parallel, and then we just project it backward. And that is where our virtual image is in this case. This would be, I think I said this in the previous lecture about this too, that this would be the kind of situation where you are looking at like a magnifying glass. Like you're looking at something small through the magnifying glass, and it's closer, the object you're looking at is closer than the focal point. So the lens makes it look really big. It magnifies it. The name makes sense. Okay, so here we have another diverging lens. Starting with red, it enters parallel through the principal axis, and exits as if it came from the focal point. So this is where it went in the red lens for a red ray for a diverging lens will go in parallel. That's what all of the red rays do. But it looks like instead of it coming, or instead of it going toward the far focal point, it looks like it came from the near focal point. That's the difference with the divergence. And blue, just the same every time. That's a nice one, reliable. And then purple, so it enters toward the far focal point and then comes out parallel, and we project backwards. So this is like going in as if it's going to hit this focal point. If the lens wasn't there, it would, but the lens diverges it. We project backward, and there is our image. Another, I was going to say imaginary, which is also true, virtual image. Okay, we were talking about those again because it relates to vision. So let's talk vision. So here is an eye. The most important parts for our understanding of vision are the cornea, this part, the lens, this part, and the retina, which is like this yellow part. The whole like thin yellow part is the retina. So let's look at how this works. Because our eyes have a lens, like the lenses we've already been talking about. I mean, obviously, like a little bit different, but it works the same way. And when we view an object, a tree in this case, the light goes in through the eye, through the lens. It's diffracted or converged. And what actually happens, because our eyes work like a converging lens with an object outside the focal point. So like our very first example of a ray diagram. The image actually ends up upside down on the retina, but our brains are able to process that information and then kind of like make it appear upright for us. Oh, and these are obviously different ray diagrams than the ones we've been making, because we're looking at both the top and bottom of the object. We've mainly just gone from the top of the object, but it's the same. So for or this is showing how the lens in your eye has to adjust when viewing an object that is far away and one that is close by. DO here is the object distance. That's why it's an O. And DI is the image distance, which is the same. It's like a standard. It doesn't change. It's just due to your eye, and it's about 2 centimeters for every one's eyes. So when you're looking at a near or far image, the muscles object. The muscles around the lens adjust depending on how close it is. And this actually changes the focal length of the eye to adjust for object distance. So for far away objects, our eyes are more relaxed. And for near objects, our eyes have to adjust in order to make sure the rays converge on the retina. So you might, if you've been to an optometrist, or maybe you just heard this, I've heard this because I do not have perfect vision. But the suggestion to every once in a while, like especially if you work on a computer or something, to look off into the distance, because that relaxes your eye, because it's easier to look at distant objects. It's easier on the eye than close objects. So here are examples of eyes that require vision correction. There's myopia, which is nearsightedness. You can see things that are nearby, but not far away. And then there's hyperopia, which is farsightedness. So you can see things that are far away, but not nearby. And this diagram shows the common reasons for these conditions. So for myopia, it could be that the lens is too strong and it bends the rays too early so that they converge before they reach the retina. Because remember, It needs to converge at the retina because that's like what sees the thing. Um, or the eye could be too long, and so maybe it's converging at the right spot, but then the eye is longer than it should be, so it's still not converging on the retina. For hyperopia, the lens may not bend the rays enough so that it won't converge by the time it reaches the retina. So see, it looks like it's going to converge like back farther than the retina, which means you're not going to be able to see the image here. Or the eye could be too short. And the same thing. It's like the lens bends the rays the right amount, but the eye isn't long enough for those rays to converge on the retina. They all have the same problem. These versions of like eyes that need vision correction or corrective lenses is that the rays don't converge to form an image on the retina of the eye. And all of these can be corrected with lenses. So for nearsightedness or myopia, we use a diverging lens that creates the image closer to the eye in the region that the nearsighted person can see. It corrects for the lens of the eye bending rays too much, or for them converging before they reach the retina. Because it's a diverging lens, it diverges the rays slightly or enough so that they will meet, converge on the retina where the image will appear. So you can see the pink here is like the original rays that come in kind of like as if there was no lens here. They just come in and they are bent too much, so they converge too early. But then when you have a diverging lens, that diverges the rays just enough so that they converge at exactly the right spot. So for nearsighted eyes, rays converge before the retina, and we use diverging lenses to correct for that. And then for farsighted or hyperopia, we use converging lenses because as we can see at the top here, so this is the other version of the diagram where again, pink is what originally happens without corrective lenses, and the blue is with corrective lenses. So we can see that originally the lens of our eye is not bending the rays quite enough. They're going to converge too late, too far. They will not converge on the retina, so you won't be able to see the image. But the converging lenses kind of pinches those converges the rays, but like kind of pinches them a little closer together so that the weaker lens of the eye is able to bring the rays together on the retina. And this, the lens is creating an object further away from the eye in the area that the eye can see. So far-sighted eyes, the rays converge after the retina. Nearsighted, they converge before the retina. And for far-sighted eyes, we would use converging lenses. And in this case, this is an example where our object is closer to the lens than the focal point, so that the image is farther away in the range where the person, whoever they are, can see it. Like they're able to see objects at that distance. And again, they're viewing these objects through the lens. So because these are virtual images, they're images that are on the same side as of the lens as the object. You have to look through the lens to see them. And that's why, I mean, that makes sense for glasses. That's why you wear them on your eyes so that you're constantly looking at everything through your lenses. Okay, that is all for this one. Have a great day.